Yay, okay, that worked. 2.7, implicit differentiation. Y'all have heard the word implicit before. What does implicit mean? Just in a non-math context. Not explicit. Okay. So then what does explicit mean? Does it mean like rapper lyrics on an album you can't buy without your parents being around? Explicit lyrics? What do explicit lyrics mean? Does it mean that explicit means cuss words? No, that's not what explicit means. Explicit just means that the lyrics, if they were explicit lyrics, leave no doubt as to what the artist is trying to convey, right? There's no interpreting. Oh, when he said it like that, he really means that, right? That's what explicit means, okay? And usually curse words kind of add the emphasis needed to make something really overt and obvious, okay? So that's what explicit means. Implicit then would be more subtle, right? A little more covert. So it'd be like if you're trying to insult somebody explicitly, you can imagine how to do that. But you can insult them implicitly by saying, yo, read between the lines, right? You remember that one? Read between the lines? Remember that one? Or maybe it's this way, read between the lines? Okay. That's implicit. They'll be like, what? What does he mean? Oh, I get it. That's implicitly. So we are going to differentiate implicitly, which means we're going to be taking the derivative kind of like in a method that we're not real sure about. No. Okay, let me show you what it means to be explicit versus implicit in calculus class. When you have an equation that is solved for y as a function of x, you get what's called the explicit form. Let's write that up above. It means solved for y as a function of x. You get y equals f of x. So it means you not only have y equals, but on the right side, you only have x's or numbers or functions or operational symbols, but you certainly don't have any y's over there. That's what explicit form means. If you take y equals 2 over x, though, and multiply both sides by x, you get an equivalent equation, right? X times y equals 2. The same information is contained inside here as was in the other one, but because this one is not solved for y as a function of x, we call it implicit form. So what we're going to learn to do in this section is to take the derivative of something that looks like this, that is not solved for y as a function of x. We already know how to solve explicit form type equations, right? That's the power rule and the sine and cosine rule and all the others that we've learned. So before we start, though, doing that, just a couple of bullet points here. d dx, remember, is the verb. When you take the derivative of y with respect to x, you write it as the derivative of y with respect to x. Same thing. You're just essentially sliding the y into the numerator, and you get dy dx. When you take the derivative of x with respect to x, of course, we've been calling it 1, and it's still 1, but it's 1 because it becomes dx dx. dx divided by dx is 1. dy divided by dx is not 1 because y and x are different, okay? So this is really what we've been doing the whole time we've been taking the derivative of x. We've been actually using the chain rule and putting dx dx, but not writing it down. So let me show you how this is going to work. Example 1. It says, find the derivative dy dx of 2 over x, doing the way we know how, which is called explicit differentiation, although you don't need to call it that. So what would I need to do to take the derivative of this? Do you want to use the Hody-High rule? What? Yeah, okay, let's rewrite it. Y equals 2 times x to the negative first. Now that's still explicitly solved for y as a function of x. The derivative of both sides, I'm going to go ahead and show this, which is what we did on the very first one we learned the power rule on, but I want to show you what we're actually doing. What is the derivative of y with respect to x on this side? It's dy dx, good. And over here, we've actually been doing the chain rule. What is the derivative of 2x to the negative first? Well, you think of x as being a blob. What's the derivative of 2 blob to the negative first? Negative 2 blob to the negative second, and we rewrite the blob, and then times the derivative of the blob with respect to x. That's what we've been doing. Okay? I then multiplied by the derivative of x with respect to x. We haven't been writing that, though, because, again, what is dx divided by dx? It's 1, okay? So we don't have to bother writing it. So we end up now cleaning it up with dy dx equals negative 2 over x squared. All right. So now what we're going to do on example 2 is I'm going to show you now how to take the derivative of xy equals 2 in implicit form. We still want, in the end, we still want dy dx. I still want the derivative function that allows me to find the slope of the tangent line for y in terms of x. But I'm starting off with xy equals 2. Okay, so here we go. Step 1 is the same. Take the derivative of both sides with respect to x. Now on the left side, because I have x times y, I've got to use the what rule? Product rule. So here we go. The derivative of x is what? 1 times the chain rule dx dx. Do we need to put dx dx though? No. Here's what I'm actually going to do. Instead of calling it 1, just kind of go along with me here. The derivative of x with respect to x is dx dx times y goes along for the ride plus x goes along for the ride times dy dx. And of course, on the right-hand side, the derivative of 2 is d2 dx, if you want to call it that, but constants don't change, so you can call it 0 with respect to any variable, really. All right, so we have dx dxy plus x dy dx. But of course, what is dx dx equal to? 1. So again, we don't have to show it, but we do have to show dy dx because dy dx is not equal to 1. So there's the derivative part, but now guess what we have to do? Since we still want dy dx, we have to algebraically solve for dy dx now. So if I subtract y from both sides and divide through by x, we get dy dx equals negative y over x. And if you compare that to what we got up here, they are exactly the not same. That's kind of weird. In calculus, if you do something a different way, you should get the same answer either way, right? Well, how come we didn't get the same answer? Yeah, well, let's look what we have here. We actually have a derivative equation still, but notice it does have an x and a y in it. So if you were going to be evaluating the slope now of the equation xy equals 2, you would have to know what not just the x is, but also what the y value is. So here's how you can make it match the other one, which is preferable because it only is a function of x. You could then take xy equals 2, and you could solve it for y after you took the derivative, 2 over x. If you then substitute that in, you're going to get dy dx equals negative 2 over x, that's what y is equal to, all over x, bless you, which of course simplifies to negative 2 over x squared. So if you were after then a derivative as a function of x, which way was easier? Differentiating explicitly or differentiating implicitly and then solving for y anyway and plugging in? Yeah, this is the easy way to do it. So when you can solve an equation for y as a function of x, you're going to want to do that. You're going to want to do that because I just illustrated that it's a lot easier. You will get the same answer, hopefully, if you do everything correctly, but it's a lot more work. So why do we even have to know how to differentiate implicitly? Because not everything can be solved for y. Well, if you're talking about a function of x that passes the vertical line test, sure, you're going to be able to solve for y. But we may have a curve that doesn't pass the vertical line test. It may look something like this. Okay? You may want to figure out, hey, what is the slope of this graph right there? It's not a function of x. That snake fails the vertical line test. But you still might want to know, hey, how fast is the snake's skin changing right there? Well, first of all, notice that if I just listed the x value, call it x equals c, that's not going to be enough to pinpoint which point I want to find the slope at, right? Because for this x value, there's 1, 2, 3, 4, 5, 6 different y values. So for things that are not function of x, They're not going to pass the vertical line test. That's why you're going to have a way to find an equation to give you that slope, but the derivative, dy dx, is usually a function of both x and y. And it's for that reason. You don't just get by with an x value, you need the y value as well. So now if I told you x equals c and y equals that one, you're like, oh, that's the place you want, okay? So not everything is going to be a vertical line function of x. We have curves now. So that's why we learn implicit differentiation. Okay, sweet. Let's define then what implicit differentiation is. Implicit differentiation is nothing more than finding the derivative of y with respect to x on an equation that is not explicitly solved for y as a function of x. And it requires the use of the chain rule, which is why we learn this after the chain rule. So let's look at an example that's a little bit more meaningful in the sense that we have to differentiate implicitly. We don't have the option of solving for y. So if you look at example 3, it says y equals x plus secant of y. Find dy dx. Now, if you look at it very quickly, it looks like it could be solved for y as a function of x, right? It's y equals. It's solved for y. But what do you notice about the right-hand side? There's a y over there, okay? So in the end, it's going to be easier to solve for y and take the derivative if it can be done. So your first step when it's not solved for y is to quickly check, can it be solved for y? Freeing this y from inside the secant is going to require taking the arcsecant of both sides once you isolate it. But then taking the arcsecant of that to free that y is going to trap the y on the left now behind an arcsecant. And that's not good. So how would you free it from behind the arcsecant? You would take the secant of both sides, which now traps this guy again. So essentially, freeing this guy traps that guy and vice versa. So you think we're going to be able to solve for y? No. But if I want to find dy dx, maybe I don't have to solve for y. If there was a way to take the derivative of this as it stood. Anyone have an idea? Implicit differentiation. Good suggestion. Let's try it. Now, for implicit differentiation, your first step for the derivative process is actually to take the derivative of both sides with respect to x. If you were taking the derivative explicitly, you don't need to do that because when you go straight from the first line to dy dx, it's implied that you're taking the derivative of both sides with respect to x. But because I haven't explicitly solved for y, that's your first step. d dx of the left side, d dx of the right side. Now, on the left side, what is the derivative of y with respect to x? dy dx. Or, if you want to use the chain rule, it's the following. It's the derivative of y, which is 1, times the chain rule dy dx. So yeah, just dy dx will suffice. On the other side, what is the derivative of x with respect to x? dx dx, also known as 1. All right, so I'm not going to write dx dx. We don't need to, it's 1. Plus, now we have secant of blob over there. What's the derivative of secant of blob? Secant blob, tangent blob, times the chain rule, the derivative of the blob with respect to x, which is dy dx. So there you go. The way you take the derivative implicitly is this with respect to x. Anything that's an x in the equation is going to be taking the derivative the normal way. But if there's a y in the equation, you're going to first take the derivative like you would in x. Secant of x would be secant x tangent x. X would become 1. But you're going to multiply, before you leave that term, by dy dx. Okay? That's the chain rule, dy dx. So you can take inventory beforehand. How many y's do you have in your original equation? 1 on the left, 1 on the right for a total of 2. That means you should have 2 dy dx's in your final answer. 1 over here, 1 over there. It's kind of nice to take inventory. Now, we're not done. We're not done. If you can't solve for y as a function of x, not a big deal. You should always be able to solve for dy dx, though, as a function of either x or y or both, because it should be linear in terms of dy dx. So the next thing you're going to do is algebraically collect like terms on the left and constants on the right. So anything with a dy dx is going to come over to the left. So dy dx is already there, and he welcomes his new friend, which becomes negative secant of y tangent of y times dy dx. And on the right-hand side, we left 1 all alone. I think that's how he prefers it. Now, how do I get 2 dy dx's in 2 terms into a single dy dx so that I can solve for it? Factor it out. Yeah, factor it out. Very good. So that's the next step pretty much every time. Collect them, factor out of dy dx, and when you factor it out of itself, you're left with what? 0 or 1? 1. I see a lot of people put 0 there. Be careful. Minus secant of y, tangent of y. Which, if you try to pronounce that as a word, that's kind of weird, right? Sexy-tanny or something like that? Secky-tanny. Secky-tanny. Suffering. Secky-tanny. I don't know. Failed Sylvester quote. What do we do now? Divide. So we get dy dx is 1 over 1 minus secky-tanny. And you're done. Now notice this derivative of y in terms of x is only a function of y. So the x value doesn't really matter. So what that tells you, if you kind of think back then, if the derivative only depends upon y, then your function is not a function of y in terms of x, but rather it's a function of x in terms of y. So the graph of whatever we started with doesn't pass the vertical line test, but it should pass the horizontal line test. Okay, it is interesting. Now, we can't graph this on our calculator to see what the graph looks like. Why? Yeah, the calculator requires you to solve it for y as a function of x. But you can do the following. You can go to the World Wide Web. Yeah, and you can go to Wolfram Alpha. And if you go to their plotting and graphics page, right here it says equations. Plot the solution to equations in 2 variables. So let's do that. I'll just type it in. You leave the plot there, and then you type in y equals x plus secant parentheses y. There it is. Now look what happens. If you hit the equal sign, it's going to be like you opened a can of Sprite. Check out right in here. It's going to be like you opened a can of Sprite. Ready? Oh, yeah, that looks just like Sprite. That didn't do it. Oh, man. Normally, it effervesces right there. It like boils and rumbles a little bit as it's coming up with the graph. I lied to you now. Okay, so notice this is the graph of not the function, but the graph of the equation. And it does pass the horizontal line test, although it doesn't pass the vertical line test. All right? So, for instance, if you wanted to know what the slope of this graph is right there when the graph crosses the x-axis, here's the tangent line surfer right here. It's going to be some positive number, right? And I put my meter stick right there at this little x-intercept. It looks like it might be what, if you had to approximate it just from my awesome meter stick skills. Probably, it looks almost like a 45, doesn't it? Well, guess what? We can actually find its bless you numeric value. Let's go ahead and do that. Very good. When you're going to plug into Leibniz notation, though, unlike function notation, you use the evaluation bar, the when bar, and we're going to plug in a 0 for y. That's going to give us the slope of the graph, not the function, but the graph on the x-axis. So let's plug it in. You get 1 over 1 minus, what's secant of 0? 1. Very good. What's tangent of 0? 0. Good. So we end up with 1 over 1, which is 1. Y'all were right. Y'all were right. That was good teamwork. I had an awesome job holding it there at the slope of 1, and y'all were good at discerning that that was the slope. We just proved it algebraically or calculusly. Is that an adverb? Calculusly? How'd you do that? I did it calculusly. It is now, sure. We showed the slope was 1. So there you go. Pretty cool. Pretty cool. Your derivative, again, will sometimes be just in terms of y, like in this case, but most of the time it's in terms of x and y. We'll see one like that here coming up. You could put x equals something, y equals something, like that, or you can just list it as an ordered pair. Okay. All right. So any questions on the first one? So far, so good. So good so far. Implicit differentiation. All right. Letter 4. Find the slope of this graph at 1, -3 by finding dy dx first and then plugging in. Okay. So you walk up to the problem. You're like, "What's up, problem?" And it doesn't answer back because it's inanimate. Is it solved for y as a function of x? No. So now you ask yourself, can it be solved for y as a function of x? Yes, it can. It can. Okay? But it's going to require the cubic formula. There's a quadratic formula. There's a cubic formula. There's even a quartic formula. But there's no quintic and above. Thank you, Niels Heinrich Abel, for proving that. Does anyone in here know the cubic formula? You got the quadratic formula tattooed on your skin in Algebra 1. So everyone still knows that one. Or you can reference it. Do you know the cubic formula? No? Did he? If you were going to get the tattoo of the cubic formula, you might need to bring your buddy with you just to have enough skin to put it on. Especially with the quartic formula, bring your whole family, because that's going to take some skin. All right? It's pretty long, it's pretty ugly, it's pretty arduous. So yes, you could verify it does exist. But, yeah, there you go. OMG was the reaction. So when do we use implicit differentiation? When it is physically impossible to solve for y as a function of x, or when we're too lazy to do it, right? Or it just becomes a little bit prohibitive to do so. All right, so let's go ahead and find the derivative. How? Implicitly. So first step is d dx of the left side, y cubed plus y squared minus 5y minus x squared equals d dx of -4. That's always step 1. I'll be looking for it, so make sure you have it. And by the way, d dx goes in front of each expression, not on the back side of it. That's like multiplication. This is an operation. All right, so how many y's do we have in our expression? You can shuffle terms around before you start. That's fine. I'm just going to do it afterwards. Yeah, no, just like representatives in each term. Yeah, there's 3 representative y's in each term. So guess how many dy dx's you should have in your final answer? 3. Yeah. Once you take the derivative, you should have 3. So here we go. From left to right, what's the derivative of y cubed? 3y squared, or blob cubed, if you want to do that. It's 3 blob squared times the chain rule, the derivative of y with respect to x. So again, here's all you have to do. Just take the derivative of y like you normally would for x, but multiply before you go to the next one by dy dx. You're going to tag it with the dy dx. Plus y squared becomes 2y times dy dx. Boom. Minus the derivative of 5y is just 5 times the chain rule, dy dx. Minus the derivative of x squared is 2x times dx. Do we want to write it? Go ahead. I'm not going to. We don't need to, but you certainly can. And on the right-hand side, d-4 of x is just 0. Constants don't change. So their measure of change is always 0. All right, now if you would have gotten rid of the x squared in the beginning, Colin said, since you're trying to solve for dy dx, and the y's are what generate those dy dx's, you could rearrange your terms before you took the derivative, taking the x squared to the right-hand side. But notice, it's just as easy here to take the -2x to the right-hand side. So it's just a matter of preference when you want to do that. I'm going to go ahead and do 2 steps in 1. My 3 dy dx fellas are already on the left side together. So I'm going to go ahead and just factor out a dy dx. And that leaves me with a 3y squared plus a 2y minus a 5. The -2x now is going to go to the right side and become positive 2x. And then the last step is just to divide through by that wonderful thing. And you're left with dy dx equals 2x all over 3y squared plus 2 times y minus 5. And there's a handsome looking derivative. Now notice it's in terms of x and y. So for the first time we see a function that not only doesn't pass the vertical line test, but it won't pass the horizontal line test. This was asking us to find the slope of the graph at 1, negative 3. So thank goodness they gave us the y value there. Otherwise, we'd be like, okay, there's several different y values at 1. We got the one located. It's the one at 1, comma, negative 3. So here's how you would write it in Leibniz notation. The easiest way is just to say at 1, negative 3, like that. Kind of write it as a footnote, almost on the evaluation bar. Or you could say when x equals 1 and y equals negative 3. That's just a little bit more writing. So I'll go back to the other way. 1, negative 3. And now we carefully plug in. Every x becomes 1, every y becomes negative 3. We're left with 2 over 27 minus 6 minus 5. What ends up being 2/16, also known as 1/8. So whatever that graph looks like, whatever it looks like, at that ordered pair, 1, negative 3, the graph is doing what? Increasing or decreasing from left to right? It's increasing, but not very much, right? It's pretty flat. Up 1 over 8. Most of the energy is translated horizontally. I wonder what that graph looks like. Whoa, as he trips into his chair. Teamwork, teamwork. All right. Let's come back up here. And again, you could go to Wolfram Alpha graphs and plots. I'm going to type in, let's see, we got y cubed. So you use the caret for that, plus y squared, minus 5y, minus x squared, and then equals negative 4. Let's see if it effervesces this time. I don't want to look like a fool. Oh, no, it's not. They got rid of the effervescence, and they just replaced it with computing. That's kind of boring. Boy, it's taken a while. Oh, there it is. It emerged. It emerged. Okay, so let's go to the point 1, negative 3. 1, negative 3 is going to be, well, there's 1. If you go down, it's going to be right down here, just to the right of the bottom part. So it'll be somewhere in there. Is that reasonable to think the slope is positive 1/8? Yeah, very reasonable. In fact, it's spot on exact. Yeah. So notice this graph fails the vertical line test, also fails the horizontal line test. Kind of looks like a cross-section of a fancy vase that would fall over. Yeah, this is rounded. Or a nose, someone's nose. Yeah, you can maybe angry eyes right there, huh? Coming off those eyebrows. Yeah, angry eyes. Okay. Pretty nifty, huh? Now, example 5. Let's look at example 5. It's kind of the same, except now it says evaluate the same derivative at the exact same point, but this time plug in before you solve for dy dx. So if you want to come back up here on the line where we took the derivative right here, the algebra wasn't too bad because the dy dx's were already on the right side. Later on, we might have to distribute first to collect like terms, but in this case, it was pretty easy. But if you know that you are only after a numeric slope, you only want the slope at a point, and you don't have to find dy dx, it's going to be a little bit faster and easier to plug in first and then solve for dy dx than to solve for dy dx and then plug in. Now, there is no way to show that you're going from this variable line to the plug-in line, so the best way to communicate that is just to say something like at 1, negative 3. You always want to signal your intention, and if you can't do it with function notation or Leibniz notation, you just say it like that, at 1, negative 3, which says, hey, I'm about to plug in a 1 for x and a negative 3 for y. You end up with 27 dy dx, and then you end up with minus 6 dy dx, and then minus 5 dy dx, and then that equals, I'll plug it in, you get a positive 6 over here and a negative 6 over there. Oh, I'm sorry, a 1. You get a negative 1 over here, and you get a positive, well, sorry, you get a negative 2 on this side when you plug in a 1. When you bring it across, it becomes positive. Now, notice we don't have to factor out the dy dx like we did on the previous example, because we plugged in all those variables that were different, that were attached with the dy dx's, we made them all like terms now. And that's why plugging in first makes a little bit more sense if you don't ever have to find dy dx. 27 minus 6 minus 5 is now just 16 of those guys, dy dx's. And now, of course, if you, let's bring the 16 across, you get 2/16, which is 1/8. Yeah. It's a lot easier, yeah. But when would you have to do it the first way? Well, sometimes if it's a free response, it might say, verify or show that dy dx equals this. And that's a lot of times how they do it. They'll give you what dy dx is equal to, and they say, show that dy dx equals this. So you have to provide all the work, and then you algebraically have to manipulate it with all the variables to get it to equal dy dx. But if the instructions are just like, what's the slope of this graph at this point? Or it's a multiple choice question, and they're looking for the numeric slope, then it's easier to plug in before solving for dy dx. It's just a little bit less algebra. Things combine a lot more quickly when you plug in first. So just keep that in mind. Okay. Let's look at example 6. Okay. It says find the derivative of y with respect to x at x equals 1 for this equation. For that equation. All right. Is your equation solved for y? No. Can it be solved for y? Actually, it can. It's a quadratic. You would actually have to write it in descending order. Y squared minus 2xy and then plus x. Your a value in your quadratic formula would be 1. Your b value in the quadratic formula would be negative 2x. And your c value in the quadratic formula would be x. But if you did it that way, how many equations would you end up having? 2, right? The quadratic formula has plus or minus. Do you want to work with 2 equations and do all this work? No. Especially when there's a way to do it without having to do that, all right? Implicitly. So let's do it Colin's way now. Colin recommended last time, since we're going to collect y's anyway on one side, let's just bring the y squared across and call it x equals 2xy minus y squared. Okay, we'll just see if this kind of shaves any labor off the algebra. Now we'll go ahead and take the derivative of both sides with respect to x. We get x, and we get 2xy minus y squared. All right, so the left side, what's the derivative of x with respect to x? Dx dx, or 1. Sweet. Now on the right-hand side, 2xy, we're going to have to use the what rule? Product rule, yeah. So the derivative of 2x is 2 times y goes along for the ride, plus 2x goes along for the ride now times the chain rule, the derivative of y with respect to x, or 1 times dy dx. So that's the red terms right there. And now we're back to the last term. What's the derivative of y squared? 2y times dy dx. So again, before you move on, just make sure you did it right. You had 2 y's in your original expression in 2 different terms, and you have 2 dy dx's. So pretty good indication that you did it correctly. Now I'm going to go ahead and bring the 2y across. It becomes 1 minus 2y. And then that leaves these guys by themselves on the right-hand side. So now I'll factor out the dy dx. And you get 2x minus 2y. And then to finish it off here, you divide through, and you end up with 1 minus 2y all over 2x minus 2y. Now let's say this was a multiple choice question, and all of your answer choices were in variable form. You know you did it right. You don't make mistakes. You've been practicing like crazy at home, at your house. I almost said house, but I said home. And you hear how it came out? Home. Okay. But you look on the test, and that's not an answer choice. What happens? Do you panic? Does your amygdala flare up? Does your reptilian brain take over? No. If you collect your dy dx's on one side versus another, you may have all of the signs in your ratio the opposite. So is it legal then to simply just commute the numerator and commute the denominator? Is subtraction commutative? Is 1 minus 2y the same as 2y minus 1? No. Is 2x minus 2y the same as 2y minus 2x? No, but is it legal when you have their ratio? Yes. It's essentially like multiplying by -1 over -1. It changes all the signs. So if you find that your answer is not there, just realize that you could change all the signs and all the terms in both the numerator and denominator, and it'll end up being the exact same thing. Okay, now I kind of broke my own rule, because I just told you on the previous example, if you're only after a numeric slope, plug in first. It just asked us to find dy dx at x equals 1, and I did not plug in first. But there was a reason for that. I can go ahead and plug in now. dy dx evaluated at x equals 1. So when I plug in, I get... Whoa. Apparently, the derivative equation formula thingy requires not just the x value, but also the y value. So let's back up. When you are not given the y value for something that's not solved for y as a function of x, it could be for two reasons. It could be reason number one, that's their hint at telling you you should solve this for y as a function of x before you start. Because it would be like xy equals 2, the way we started. You would want to solve it for y. But we already thought about that, and it can't be done very easily. So that's not the reason why here. The other reason could be that even though this graph would fail the vertical line test, which means for any given x there might be multiple y values, at this value of x, there's probably only one y value associated with it, and you're just going to have to find it. So that's the case here, because we can't solve for y. So plug in the 1 into your function and see what y value you get. So at x equals 1, you get the original equation is y squared plus 1 equals 2y. Well, now it's a quadratic in terms of y. So bring it across, y squared minus 2y plus 1 equals 0. Now the squared there tells you that for any value of x, there might be two y values. If there were two y values, which slope do we want? Well, let's ask that question later, possibly. Let's factor this. This factors into y minus 1 times y minus 1. Also known as y minus 1 what? Squared. So what's the only y value associated with that x value? 1. So you happen to be at a point on the graph where there is only one y value. And now we're going to have to find it. So really the point is now 1, 1. You're not going to be given just the x value if there's more than one y value. It's going to either be something you should be solving for y in the beginning with, or when you plug in, you get a single solution. So now I'll come down here, and I'll put at the point 1, 1. Now when I plug in a 1 for x and a 1 for y, carefully so you don't get them backwards, you get 2 times 1 minus 1 is 1. All over 2 minus 2. Uh-oh. Apparently the derivative is not defined there. Why, though? Well, yeah, if you were to graph the derivative, you would have a vertical asymptote there, which means what? What does 1 over 0 really mean? It means some type of what? It means some type of infinity. Right? 1 over 0 means vertical asymptote. The graph is going to force the values to infinity or negative infinity. So if your slopes, dy dx, are approaching infinity, what type of tangent line do you have there? You have a vertical tangent line. Good. A vertical tangent line at x equals, or at the point 1, 1. You have a vertical tangent line at the point 1, 1. So the function value doesn't exist. The graph of the derivative would have a vertical asymptote there, but that also means, more importantly, that the derivative values or the slope values will be forced up to infinity or negative infinity. Let's see what the graph looks like. Apparently at 1, 1, there's a vertical tangent. We just kind of stumbled across that, kind of by a happy accident, to use Bob Ross's terminology. Okay, so typing this guy into the Wolfram monster, y squared plus x equals 2xy. I wish it would ever effervesce just for old time's sake. Nope, not going to happen. Come on. Work it, work it, work it. It's getting close. Ooh, it identified it as a hyperbola. There it is. Okay, it is a hyperbola. Let's look at the point 1, 1 on the graph. The point 1, 1. You go right 1, you go up 1, and notice it appears to be a what right there on the very edge? Vertical tangent line, yeah. If you were to come into the right, now you're back to failing the vertical line test. Now at that x value, there'd be 2 y values. But right there at the very, very edge, we have a vertical tangent line, okay? There's another vertical tangent line on this graph. Can you spot where it is? It appears to be at the origin, right? Now, let me kind of add something to this question here. One of the important things, or one of the common things you're going to be asked to do once you have your implicit derivative equation is you're going to be asked to determine the following. Where does that graph have horizontal tangents, and where does it have vertical tangents, okay? And it's usually going to be a ratio. So in a ratio, you get horizontal tangents when the derivative is equal to 0, which means the ratio is going to be 0 over non-zero. So just when the numerator is 0, you're going to get horizontal tangent lines. Similarly, as we just saw, if the denominator is 0, just the denominator, you get vertical tangents. If you stumble across a value that gives you a 0 in the top and the 0 in the bottom, now the derivative is failing to exist, not because it's vertical, but because it's not there at all. So you would throw out any value that causes a 0 in the top and the bottom. So just zeros in the top, horizontal tangents. Just zeros in the bottom, vertical tangents. So let's do this. Let's take our little handsome derivative, the one I highlighted, copy him, and come over here. And let's go ahead and answer the question. Let's pretend we were asked at what x values does the graph of the equation that was given, it doesn't have a name because it's not a function, where does it have vertical tangent lines? Maybe this is a free response question on your test next Wednesday. So the first thing you need to do is say dy dx, because it's a ratio, equals non-zero over 0. Okay? No, don't just say d and e. If you want to say something other than non-zero over 0, say it equals plus or minus infinity. But don't just say d and e. Because remember, 0 over 0 is d and e, but for a different reason. So that's going to get you a check if you say dy dx equals non-zero over 0. But then what do? You take your denominator, 2y minus 2x, and you set it equal to 0. Now in this case, because there's 2 unknowns in this one equation, there's not a unique solution, is there? There's infinitely many. So here's what you're going to do. If you ever end up at this point with 2 variables, all you're going to have to do is solve for either variable, whichever one is easier. Well, it's just as easy to solve for x as it is for y. What you're going to do after you solve is you're going to plug it back into the original. Would you rather plug in for x or plug in for y? I'd rather plug in for x, because if I'm plugging in for y, I'm going to have to square it. So that informs your decision here. So 2y equals 2x. If I solve for x by dividing through by 2, I get x equals y. As opposed to solving for y equals x. Yeah, it worked out okay. So now what you're doing is you're taking that and you're plugging it in right there. So everywhere there is an x, you're going to plug in a y. So you get y squared plus x, which now is another y, equals 2xy, which is 2yy, or 2y squared. Now I'm going to get everything on the left side. So I get a 0 on the right. 2y squared minus 1y squared is y squared, and then I get minus y. You don't want to divide out the y's. You don't want to factor a y out of both sides and divide it out. Remember, when you lose variables, you lose information. So rather, factor it now. Pulling out the y, you're left with y minus 1. So now you know at least the y values where you have vertical tangent lines, at y equals 0 and at y equals 1. Now all you have to do to find the x values that go with them are plug each of those y values back into one of 2 places. You can either plug those y values back into the original equation, or because it's a system of equations, you can plug it back into here. I think I'd rather plug back into here because it's easier. So if y is 0, what is x? 0. So the actual points Sometimes we just get the x values and the y values. But in this case, the actual points are 0, 0, and 1, 1. Well, we already knew 1, 1 was the solution because we kind of stumbled over that one earlier. And we already looked at the graph, and y'all told me that the other one was at the origin, because visually you could tell, and we just verified that it is, in fact, at the origin. So that's pretty darn cool. So we'll be doing more of that later on. But just to recap, if you want to know where the tangent lines are vertical, just set the denominator equal to 0. If it has two unknowns in it, solve it for either variable, plug it back into the original one, and then solve from there. Okay, how much time do we got? 10 minutes? Okay. I'm going to go ahead and start example 7, and then we may have to stop for a pledge. The graph of the equation x squared plus y squared equals 4 is a circle centered at the origin with a radius of 4. So if we go ahead and sketch the graph, if the radius is 4 and the center is at 0, just go out 2 units in either direction, and then connect the dots, or connect those points. So there it is. There's a pretty looking circle. It says to sketch the graph of the equation. Okay, it's right there. Oh, I sketched it right. I said it wrong. Yeah, 4 is equal to r squared. This number here is r squared. So the radius is 2, and the diameter is 4. Yeah, thanks for catching that. Friday the 13th. Kind of weird. All right, so now that we know the radius is 2, the center is at 0, we have it sketched. It says to find dy dx. Now, we could solve this one for y, but it's going to be plus or minus the square root of 4 minus x squared. So this one is easier. We don't have to use the quadratic formula, but still, if we did it that way, we'd have to work with how many different equations? 2. Do you want to? No, I don't either, because there's a way to do it without that. So let's just take the derivative of both sides. X squared plus y squared equals the derivative with respect to x of 4. All right, so step 1, ddx in the front on the left, ddx in the front on the right. And let's go through the derivative. On the left, the derivative of x squared is 2x times dx dx, which we don't need, plus the derivative of y squared is 2y times dy dx, which we do need. And on the right-hand side, the derivative of 4 is 0. Yep. We had one y term. We have one dy dx. It's looking good. So if you solve for dy dx in steps, bring the 2x across, it becomes negative 2x. Divide through by 2y, and you get dy dx equals negative x over y. There is the equation that gives you the slope of the tangent line at any value of x or y. It says, using calculus, verify that the graph has horizontal tangents at 0, 2, and 0, negative 2. Well, we can clearly see that there's a horizontal tangent up here, and there's a horizontal tangent down here at the bottom. But if we want to figure out where it has horizontal tangents, here's what we're going to do. dy dx is equal to what? What are we going to say? 0 over non-zero. It's a ratio. So now we're just going to take the numerator equal to 0, and I'll just throw in the negative with the x. We take the numerator and set it equal to 0, and we solve. Well, this one was easier than one we just did because when I set the numerator equal to 0, I only had one variable instead of 2. So I didn't have to take that extra step of solving and plugging back in. So when x is 0, how do you find the y values? You plug it back into the equation of the circle. So you get 0 squared, that's x squared, plus y squared equals 4. Plug it back into the original circle equation, and that gives you that y equals plus or minus 2 when you extract both square roots. So we know that the graph now has horizontal tangents at the point 0, negative 2 and 0, and that is consistent with what we had up here. 0, negative 2, 0, positive 2. All right, I'm going to stop right there on example 7b, and we'll pick up on Monday at part C, and we'll do D, and I'll actually show you kind of something neat, if you remind me especially. I'm going to show you how to get the derivative equation right there Negative x over y without using calculus. That'll be cool. That'll be really cool. I think I'm going to show up Monday just for that. Okay. Even though Monday's senior skip day. Pass it on. No, it's